Hey guys, how you doing? This is Coach Scott with Purple Wave Chemistry. Woohoo! So let's start talking about some of these ways that we're uh, using these EBDs, energy bar diagrams, to understand what's going on. And if it helps you a little bit, what we're doing is we're breaking down the different types of kinetic energy, right? And potential energy. Thermal energy, that's kinetic energy. You've got the little things moving back and forth. As they move faster, it's going to have an increase in thermal energy. Your phase energy, that's just different types of potential energy, depending on what the phase is. Chemical energy, different types of potential energy. Let's look at some of these. All right? So, I have reaction. Okay? Heating potassium chlorate. Let's see. Heating potassium chlorate powder produces, there's my arrow, potassium chloride and oxygen gas. Now heating. So let's go ahead and let's write our reaction. Of course, we've got to write down known facts. So I've got potassium. I look at my periodic table right there. Whoop, cancel. I've got my little things here, right? Potassium's in group 1, so it's got a +1 charge. I'm going to write this down here, but I'm going to erase it here in a minute. So that's just a +1. So I got to look up chlorate. It's not chloride, it's IDE, and then I'm going to look at my periodic table. And it says chlorate. So I've got to look at my chart of charges, my periodic table cheat sheet, whatever, find out what chlorate is. Okay, chlorate is ClO3. ClO3, that is a polyatomic ion. So that's got a 1 minus. Okay, I got +1, -1. I'm good. So what I want to do next is I'm going to erase this because I don't need it now. I've got my right formula, so now I can do what I've got to do. All right. So cool. Let's go ahead and let's use that one. All right. So now I'm going to draw my arrow because it says heating potassium chlorate powder produces potassium chloride. All right, so now I'm going to write my products. K +1 and Cl chloride. I know that's a -1 because it's from group 17. I'm good. All right, so I'm going to erase that. KCl, that's all it is. All right, and now my other product, oxygen gas. Oh, but I remember. Oxygen gas is not just O, it's O2 because have no fear of. It's a diatomic formula. Now I've got to write my energy in there, but I won't do that yet until I go through it. All right, so I've got my KCl3. Before I start heating it, all right, what's my thermal energy? What's my thermal energy? Think about it, I'm going to pause. Okay, so what have I got right now? Well, I don't have a lot of thermal energy. It's at room temperature. Alright, so I'm just going to put 2 bars, why not? 2 bars here. Ooh, we've almost screwed up here, guys. We've got to do something before we do anything else. We've got to balance this reaction. Alright, so I've got 1 potassium, got 1 chlorine, I'm good. Ooh, so I've got to make this, I'm going to try to make this even. So I'm going to put a 3 there. That means I got 3 oxygens. And then, of course, I need 6 oxygens, right? 3 times 2 means I need 6 oxygens on this side, put a 2 there, and a 2 there. Okay, so now I've got a balanced reaction. So anyway, back to what we were talking about with these energy diagrams. So what's my chemical energy now? Well, I don't have a lot because I had to heat it for anything to happen. So I'm just going to give that 2 bars of chemical energy. All right. So it says I heated, so this is energy flow. Inside here is the system. This is the system right here. All right. Outside the circle are the surroundings. So the surroundings, that little, the Bunsen burner, the heater, whatever, added energy or added Q, that's what we use for it, added Q to the system. And I'm going to go ahead and give that 2 bars. Why not? So this added heat to there. So these are my reactants, my cold reactants. I'll put cold there, the subscript, just so I know what I've got. So let's see, I've added 2 bars of energy. So that means my thermal energy has now got 4 bars. It's pretty hot. Okay, my chemical energy has not changed yet. And inside the system, these are very hot reactants. So we're going to say reactants, reactants, and I'm going to put hot. So that thermal energy can now start transferring some of that heat, some of that energy to the chemical energy to start breaking down, you can see that little dot there, start breaking down some of those bonds, some of those connections that are holding those atoms together. So now this energy is transferred over to the chemical energy side. Okay, this thermal energy is transferred, the energy is transferred to the chemical energy side. So now, what do we got? So now, let me go back up here to the purple so we're all consistent. Now thermal energy is down to 2 bars. Chemical energy is much higher, the potential energy there. Alright, and I'm sorry, I'm at an angle. So these are the products, right? So the products have formed 2 new things. So there's more potential energy on this side. Okay? So let's draw us a ECH curve, or an energy curve. So this is energy. Okay, let's go back up here to the yellow. Alright, so energy here, when we start, it's low. Alright, and then as it moves on, the reaction moves on, we add heat. Okay, and so now that's high. So this would be the reactants. Now that's products. So energy was added to the products. Chemical energy was added to the products. So where do we put the energy? On the product side or on the reactant side? Well, we had to add the energy here to the reactants for it to happen, for it to kick, right? So the energy is added to the reactants, assisting forming the chemical reaction to occur to form the products. Now what type is this? Is this endothermic or exothermic? It's endothermic, because energy was added into the system. Energy was added into the system right here. Okay, when that added into the system, it's now endothermic. When heating the reaction, what that means is now we've got energy that's flowing from the warmer surroundings, which could be the Bunsen burner or whatever, to the cooler system. Now, because the total energy before and after the reaction must be the same, or because, remember the law of energy conservation, energy is conserved during a chemical reaction. The chemical potential energy stored in the reactants plus the absorbed energy through heating it, okay, is equal to the chemical potential energy stored in the products. So since we added the energy here, thermal energy transferred here, it's got to be the same now. All right. So the chemical energy, the potential energy, the reactants is lower than the products. So we're going to draw 1 bar, or 2 bars for the ECH of the reactants, we threw 4 bars for the products in the bar diagram. Okay. Okay. It says heating is required for the reaction to start. The rearrangement of the atoms happens after the energy is transferred from the surroundings, all right, through the collisions between the faster surrounding molecules. Whenever we add the thermal energy, they start moving quicker, all right, and the faster molecules is added, and then the slower molecules that are just there. So we're adding energy that's stored in the ETH first, then we transfer it to the ECH, the chemical energy, when the atoms rearrange to form the products. And we do that, it increases the potential energy of the chemicals, of the products, and it decreases the thermal energy. So that's an endothermic reaction. Hopefully that helps you guys out. And we'll do some more. We'll do an exotherm later. Thanks, guys. Hullabaloo, connect, connect. All hail the Christian Brothers, Purple Wave. Have a good one. Bye.